Let's talk about the straightness tolerance. Straightness is one of the 4 form tolerances. So we have straightness, flatness, circularity, and cylindricity. They all have a few things in common, one of them being that they only apply to one feature at a time, so individual features. What this means is that they'll never have datum references in the feature control frame. So if you have feature control frame with something like perpendicularity, you're saying for one surface or axis to be perpendicular to another surface or even axis, and that other surface or axis is indicated right here with a letter. With straightness, we don't do that because something can't be straight to something else. Something can't be flat to something else. It can't be circular to something else. So the feature control frames with all of our form tolerances are going to be very bare bones, right? They're not going to have a lot of information compared to something like position, which can look like a book. I mean, they can get really long, they can be composite, so they have 2 levels on them, whereas straightness, flatness, cylindricity, and circularity tend to be a little more compact and easier to understand. So straightness specifies a tolerance zone within which the considered element of a surface or derived median line shall lie. A straightness tolerance is implied in the view where the elements to be controlled are represented by a straight line. So there's 3 ways to apply the straightness tolerance, all of which I'll talk about. There's line elements on a flat surface, line elements on a cylinder, and derived median line of a cylinder. Now, in the older versions of the ASME standard, there were ways you could use straightness on the derived median plane before the new standard where you have the ability to use flatness on a derived median plane, so you don't need that anymore. Looking at older drawings, though, if you see something kind of funny, sometimes you can go back and look at the older standards and figure out if they're applying straightness to a plane instead of a line. So the first case I'm going to talk about is the straightness of line elements on a flat surface. So with all of these, it's important to see how the feature control frame is connected to the orthographic view, because it does matter as to what tolerance applies, how you make it, and how you inspect it, okay? So if you've got a straightness tolerance that's on the extension line or on a leader line pointed to the surface, it's applying to the 2 parallel lines on this top surface in the direction indicated by the orthographic view. So what that means, on a part like this, say it's a rectangle, right? If we went to go inspect this, right, we check for size right here. It doesn't matter what this is, but say we have, 50 thou, so 100 thou of total tolerance. We have the straightness that tightens it up a good bit, 10 thou. But if we draw this part in 3D, right, I'm going to just bring it out. We only need elements to be straight within 10 thou going in this direction. And the other direction, so going toward the paper, or in this case, the whiteboard, there's no requirement for that 10 thou. It only applies in one direction, so this way. The other way, we still have that 100 thou of total tolerance. There's no requirement for it to be straight. So you can end up with parts that look like a corrugated roof, which is what I tried to capture right here. Now, it is possible, say this had a right view, right? So you're showing this in projection. You could have a totally different straightness tolerance on it. So you could say 100 thou total tolerance. You got 10 thou going this way, and a separate straightness tolerance saying 10 thou going the other way, or 5 thou, or whatever. There can be combinations, but you typically wouldn't have 2 straightness tolerances going in different perpendicular directions, because you just use a flatness tolerance and it would accomplish the same thing. So in this use, the straightness tolerance is required to be less than the size tolerance. It wouldn't make sense for the straightness tolerance to be greater because you'd be violating MMC, the boundary of perfect form. If, on the other hand, you have a specific note that says perfect form MMC is not required, or the newer versions of the standards use the interdependency symbol, which accomplishes the same thing, you can have a greater straightness tolerance than your size tolerance. When you have this situation right here as drawn, the boundary of perfect form will still apply, which just means that if this block comes in at its maximum, its MMC size, there will be no room for this tolerance. Okay, so it's not additive. You don't have, and let me put a real number here. As you approach that boundary of perfect form, you start to lose out on the straightness tolerance that you had. So if the block comes in at MMC, no straightness tolerance. If it comes in under MMC, you can start to use the straightness tolerance, but only up to 10 thou. So let's talk about our next case. So this is line elements on a cylinder. So this has kind of the same form as the other one. Notice the feature control frame is connected to an extension line, which I'll go ahead and draw it, but it could just as easily be on an extension line pointing to the surface. They mean the exact same thing, but watch out, the next example I'm going to show you, it'll be in a different place and mean a different thing. So this is similar to our rectangle a second ago, but if you notice, we've got a diameter symbol in there. So this is a cylindrical part. We check the flatness in the same way. It's still got to be less than the size tolerance because we're refining it, but we can just run the indicator going in this direction. As long as it's been 10 thou, we're good. So if it's just a pin or a cylinder, you just check one, you roll it a little, check another, roll it, check another, and just keep going until you get less than 10 thou on each individual one. Now the part could end up looking kind of like that because you have this large size tolerance, right? So it's only got to be straight in this direction. It doesn't have to be, there's no requirement for any kind of circularity on this part, right? So sometimes that's helpful, sometimes it's not. This can be used for a conical surface as well. So if it's tapered, you're just checking the straightness of each surface element. So our last use of straightness tolerance is the derived median line straightness. So there's a couple giveaways that this is different than the ones we talked about before. It's doing a different thing. So first, it's going to be adjacent to the size dimension. So usually just tucked right under it. If you notice, we have a diameter symbol in there. That's a giveaway as to the shape of the tolerance zone. It's letting us know it's a cylindrical tolerance zone in which the derived median line of this cylinder must lie. Okay, so what we're going to end up with is an imaginary cylinder inside of this part in which the derived median line of the part must lie. So the derived median line is found by measuring points and making sure that each opposing point lives inside of that area. So the derived median line straightness is allowed to violate the boundary of perfect form. What happens is that because you have that tolerance on this tolerance zone, you still have your limits of size, right? So you go through and you measure everywhere on the part. As long as it comes up with the correct number, so in this case 1.05, it's going to be good size-wise. But with that 10 thou, this ends up getting added to the maximum size. So it allows some bend in the part. This creates what's known as an outer boundary. The outer boundary is a quick way of saying the most room the part can take up. So it's a little bit different than a virtual condition. If you notice, this is applied regardless of feature size. So you're always going to have 10 thou on this derived median line tolerance, whereas in a minute I'll show you the MMC that would change depending on how the part actually came out. Let's talk about derived median line straightness applied at MMC. So when you see this, it's very similar to the one I was just talking about before. The only difference that there's a M with a circle in it in the feature control frame right behind the tolerance. So when you read this, read it as straightness tolerance with a diameter tolerance zone of 20 thou, but only at MMC. This 20 thou is only applied at MMC. If the part is not at MMC, this will be a larger number. So I can show you with a chart in a second. But let's go over MMC for an external feature. So a cylinder is going to be the largest size of that cylinder. In this case, the MMC is 1.02. So if it comes in, if we check it with calipers or whatever, and it comes in under that MMC, we get more tolerance here on this straightness equal to the amount of the departure from MMC. So I got this handy chart to kind of show us what's going on here. So the feature size is what we measure. So it'll be anywhere on the cylinder, right? So if it comes in at MMC 1.02, our diameter tolerance zone is always 10 thou. But if we measure the part and it's a little under MMC, we get more tolerance equal to that departure, okay? So the word bonus tolerance isn't used anywhere in the ASME standard, but this is what people are referring to when they talk about bonus tolerance. The next term we'll deal with, if you add the feature size and the tolerance zone, the tolerance you have on that feature, you get what's called a virtual condition. Now this only applies when you're using MMC. If you're using regardless of feature size, so nothing here, it's called the outer boundary. But if you notice, if we add these two numbers up, it's always the same. This is where hard gauging comes in. So what happens is the part gets smaller, it's allowed to bend more or have any kind of irregularities. But the idea is it'll always fit in the same size place, right? So it kind of looks like if that part came in with a diameter of 980 thou, right? We have the maximum tolerance on the derived median line of that. So it means that it can be more bent, but it still has to come in this virtual condition, this 1/30 thou. So we can check the size with calipers or whatever and make sure it meets at least the size restrictions. And then we can use a hard gauge. We can have something set to 1.03 to make sure the part is good. So the last thing I want to touch on is something called unit length straightness. So this looks like a composite frame and something like position or profile, but it isn't. If you notice right here, it's got a tolerance / a length. What this means is that you have 20 thou of derived median line straightness at MMC for the full length of the part. So we could figure out what the virtual condition for this top part of the frame is. So it's going to be the MMC plus the tolerance equals 1.04. So if we made a gauge to check the top of that feature control frame, it's going to be a gauge, the inside diameter set to this, that's 5 inches long, right? It's got to cover that there. The second gauge we have to make to check the bottom part, this is a unit length straightness. So it's saying it has to be straight to within 10 thou, but only in 1 inch increments. So the gauge for that, MMC plus the tolerance, okay. It would be a gauge with a smaller diameter, but it would be shorter because it only checks 1 inch at a time. Now, in reality, these two tolerances wouldn't be so close to each other. It probably wouldn't make sense. Maybe this one would be 20 thou and this one would be 1 thou or something. But you can imagine if you have a mechanical assembly where you have a collar that has to slide across a shaft, you really need that collar to fit pretty good while it's sliding. But if the shaft has a little bit of banana to it, it would still be able to do its thing. It doesn't have to be that straight through the whole thing. It only has to be a straight enough to fit the collar at any one place at any one given time. Okay, so that's straightness, specifying straightness per unit length.